Welcome to Efiwe, excellence without stress.
Hi, dearest Efiwe. We are back again. And it's me, Miss Stella, your favorite physics tutor. And today we're taking another very interesting topic in physics, which is work, energy, and power. Work, energy, and power. So, what is work? Work is said to be done whenever a force moves its point of application a distance in the direction of the force. It is the product of force and a distance in the direction of the force. There is a major example we give when we try to explain force. It's about two people. One person is seen pushing a wall and using a kind of power, like using all his power, using all his energy. And for example, the person is using 40 or 500 newton to push the wall. And the person that is just holding a spoon and is carrying the spoon from one point to another. Which of the two people can we say has done work? To us, the person that has done work is the person that has moved a distance, because if you check the mathematics expression for work done, let's go to our board to check for work done. For work done, we said work done. We have that work done. Is equals to what? Force times distance. So no matter the amount of force you apply, so work done, if the person, supposing the first person was applying a force of 200 newton to push a wall, and this other person was holding just a spoon but was moving about, was carrying that spoon from one point to another. This one's force was just, let's just say 10 newton. This one was applying 200 newton, the first person, but was moving in a distance of 0. Work done is 0 because the person has not moved. But this person that has moved, even though his force is so small, but the person has what? Done work. And that is the application between work done. So, work done is said to be done whenever a force moves its point of application a distance in the direction of the force. It is a product of force and a distance in the direction of the force. So, work is force times displacement. Work is a scalar quantity. The work done in lifting a body is equivalent to the work done in lifting a body is equivalent to the potential energy, that is mgh. Yes, mass. You remember that F is equals to ma, and g. Work is a vector quantity. Work is not a scalar quantity. Work is a vector quantity. The work done in lifting a body is equivalent to the potential energy, that is mgh. Recall that F is equals to ma. Recall that F is equals to ma. So when we are talking about a body that is affected by gravity, our F can be equals to m, then g. So if it is now moving a distance, that one will become height. So that's why we have it as h, and that is equals to what? Pe. Work done is equals to Pe and is equals to mgh. So, and the unit of work is joules. To summarize, we can say that no work is done if the displacement is 0. If you have not moved a distance, no work is done. If you are not applying any force, no work is done. The force and displacement are mutually perpendicular to each other. The more the force, the more distance the person covers. The more the work done. If force and distance are moving in the same thing, the force and the work done is actually increasing. Therefore, a student standing with a load on his head for 2 hours has done no work except the work he did to bring the load up. Yes, an object is horizontally dragged across the surface by 100 Newton force acting parallel to the surface. Find out the amount of work done on the force in moving the object through a distance of 8 Newton. Very simple. We have our force, we have the distance moved. So that's 100 multiplied by 8, giving us 800 joules. So energy is the ability to perform work. Energy can neither be created nor destroyed, and it can only be transformed from one form to another. The use of energy is also the same as work, which is joules. Energy is found in many things, and thus there are different types of energy. All forms of energy are either kinetic or potential. Kinetic energy is energy a body possesses by virtue of motion, then is by virtue of position. The energy in motion is known as kinetic energy, whereas potential energy is energy stored in an object and is measured by the amount of work done. Types of energy: we have mechanical energy, we have chemical, electrical, magnetic, and so many types of energy. And don't forget, the SI unit of energy is joules. Kinetic energy: kinetic energy is energy associated with the object's motion. Objects in motion are capable of causing a change or are capable of doing work. To better understand, let us think of a wrecking ball. A wrecking ball in motion is used to do work such as the demolition of buildings, stones, etc. Even a slow-moving wrecking ball is capable of causing a lot of damage to another object, such as empty house. However, a wrecking ball that is not in motion does not do any work. That is it. No matter how much power, how much things, destruction it can make, if it's not in motion, it has done no work. Another example of kinetic energy is energy associated with the constant random bouncing of the atoms or molecules. Yes, this is also known as thermal energy. The average thermal energy of a group of molecules is what we call the temperature. And when thermal energy is transferred between two objects, it is known as heat. It is known as heat. Kinetic energy is determined by Ke is equals to half mv squared. That's the formula to determine kinetic energy. Potential energy. Potential energy is energy stored in an object or system of objects. Potential energy can transform into more obvious form of kinetic energy. So potential energy is mass times acceleration due to gravity g times the height, that is mgh. Both potential energy and kinetic energy form mechanical energy. Principle of conservation of energy. In a closed system, that is a system that is isolated from its surrounding, the total energy of the system is conserved. Energy can neither be created nor destroyed, although it may be transformed from one form to another. Few examples: in a torch, the chemical energy of the batteries is converted to electrical energy, which is then converted to light and heat energy. In hydroelectric power plants, water falls on the turbines from a height. This in turn rotates the turbines and generates electricity. Hence, the potential energy of water is converted into the kinetic energy of the turbine, which is further converted into electrical energy. In a loudspeaker, electrical energy is converted to sound energy. In a microphone, sound energy is converted into electrical energy. In a generator, mechanical energy is converted into electrical energy. When fuels are burnt, chemical energy is converted into heat and light energy. Chemical energy from food is converted to thermal energy when it is broken down in the body and is used to keep it warm. So a force displacement graph will have force in Newton on the vertical axis and displacement in meter on the horizontal axis, because force displacement is giving us work. So the area of the graph is force times distance, and the quantity also represents the work done on J. What we are just trying to say there is just that if we have a force displacement graph, if this place is force and this place is what? Displacement in meter, this one is in Newton. So and we have something like this at point maybe 20 Newton, the distance covered was 5. At point 30, the distance covered was 10. At point 60, the distance covered, so you can do it like this, was 30. So we have this. So this is what is called. So if you want to know the work done at this point, it's just 20 multiplied by 5. You know, first work done is force times distance. So 20 multiplied by 5 will give us 100 joules, and that's the work done from here to here. That's the work done. So that's what we are trying to say in that statement. So power, we can define power as the rate. I've already said this countless time. Any time we hear rate, it is divided by time. There is the quantity, the next quantity divided by time. We can define power as the rate of doing work. It is the work done in unit time. SI unit of power is watt, which is joules per second. Sometimes the power of motor vehicles and other machines is given in terms of horsepower, which is approximately equal to 745.7 watts. So power is equals to work done divided by time taken. Don't forget that. And so let's derive so many formulas for power. Control delete. So we said, so that when you see parameters, you can we have that power is equals to work done, right? Work done over time. Yes, good. So power also, recall, is equals to force. Power, yes, is equals to, work done is force times distance, right? Then divided by time. Don't forget, velocity is equals to distance over time. So we can say our power is equals to force times what? Times velocity. Also, power can also be equals to mgh over T, mgh over T. So these are the formulas for power, and the different formulas we can use to solve for power depending on the parameters we were given. So power. So the unit for standard metric work is the joule, and the standard metric unit for time is the second. So the standard metric power is joules per second, defined as watt and abbreviated as W. A 60-watt bulb is switched on for 24 hours a day, and there's another 60-watt bulb that is turned off for only 12 hours. Find the energy consumed by both the bulbs in one day. We've done it in electrical energy power, where we explained that for you to know the energy consumed, it's going to be in kilowatt hour. So look at it now. For the first 12 hours, both bulbs are turned on. Therefore, power is equal to the 60 watt for the one. Okay, this one is 60 watts is switched on for 24 hours a day, while the other one is switched on for 12 hours a day. So we want to know the kilowatt first. So 60 plus 60 will give us the watt. That is 60 plus 60 is equal to what? Is equal to 120. 120 divided by 1000 will give us the kilowatt. Then kilowatt hour, then you multiply by these hours that we have. We have the first one for 24 hours, the other one for 12 hours. That's 12 times 24. That's 12 plus 24 rather. That's 36 hours. So that's 36 hours. Then 36 hours multiply. That's all we even actually need. We actually need it for that. That's all we need. So let's see now. So for the first 12 hours, both bulbs are on. Therefore, power is equal to 60 plus 60. That's 120. So energy is power times time. That's 120 times 12 hours, which gave us 1.44 kilowatt hour. 1.44 kilowatts. Now, for the next 20 hours, only bulb A is on. So what would that be? So that would be 60 watts times 12, which is 0.72 kilowatt hour. So what is, find the energy consumed by both the bulbs in one day. So the first bulb was just for 12 hours, the other one was for 24 hours. So the total energy is the addition of 1.44 plus 0.72. That is the total energy both of them consume. So we've explained this very well when we explained electrical energy and power. We've explained how to solve all of this. It is so simple. The amount you turned on your bulb for a particular day, then you add it, because this is just basically what we need. We need to know the kilowatt hour. So kilowatt hour. So you have to know the kilowatt, then multiply by that. Then if there is now money, you now calculate it by the price of the unit price, multiply by the unit price. So for example, you have a bulb. They say this bulb 60 watts, 12 hours. The second 60 watts, 24 hours. That's so simple. So I want to know the kilowatt. That's just 60 plus 60, right? So 60 plus 60, that's equals to 120. So 120 divided by 1000. 120 divided by 1000, after getting, that's your what? Kilowatts. So 120, that's 12 over 100, sorry. 12 over 100, you can also call it 4 in 25. 4 in 100. How many fours can we? No, we cannot see 4. Sorry, let me just do. We have 12 over 100. 4 over 100. We have 4 here, 3, 2, then 5. That's 25. So 3 divided by 25 kilowatts. Then this is what we now multiply by the hours. The first one 12, the second one 12, 24. So 12 plus 24. So that's 4 plus 2, 6. 2 plus 1, 3. So 36. So this will now be 3 over 25 times 26 hours. So if they now tell you that they pay 1,000 naira per unit, then you now multiply it by whatever we have here. Yeah, whatever we have there. So that is that about that. So in this scenario, the power consumed during or on the whole day varies as one bulb is turned on for only 12 hours. So we have to calculate the average power. Average power is total energy consumed divided by total time taken. Therefore, the average power for our light is, you add them together, divided by what? 24 hours. So 0.094 kilowatts per day, because we were asked to look for the amount of energy consumed in a day. So that is it. So energy and society, sources of energy. Sources of energy can be classified into renewable sources or non-renewable sources. Renewable sources of energy are available, plentiful in nature, and are sustainable. These resources of energy can be naturally replenished and are safe for the environment. These are examples of renewable energy. Examples of renewable source of energy are solar, geothermal energy, wind energy, biomass, hydropower, and tidal energy. Then we have a non-renewable resource. It's a natural resource that is found underneath the earth. This type of energy resources do not replenish at the same speed at which it is used. They take millions of years to replenish. The main example of non-renewable resources are coal, oil, and natural gas. Examples of non-renewable sources of energy are natural gas, coal, petroleum, nuclear energy, and hydrocarbon gas liquids. The resources renewable, the resources that can be renewed once they are consumed are called renewable sources of energy. These resources do not cause any environmental pollution. Renewable resources are inexhaustible. Renewable resources are not affected by human activities. Examples of renewable resources are air, water, and solar energy. We said that in the previous slide. Then we have the non-renewable resources that cannot be renewed once they are consumed. They are called non-renewable sources of energy. These resources causes environmental pollution. Non-renewable resources are exhaustible. Non-renewable resources are affected by human activities. Examples of non-renewable resources are natural gas, coal, and nuclear energy. Dams and energy production. Hydroelectric power is power generated from water, and it is one of the best methods of electric power generation. The production capacity of a dam is dependent on the water supply available. Once constructed, a hydropower plant will be operational for decades and provides the water source don't run out. It can produce electricity at a constant rate, as mentioned earlier. The output can be easily controlled. Dams also have a couple of problems though. Dams are very expensive to build, and to last decades they must be built on a high standard, up to a high standard. Although in the case of dam breaches, the runaway water will cause significant flooding in the downstream regions. Also, the creation of a reservoir causes a massive tract of land to get submerged. This area is lost, and people living in such areas are displaced. And this is it. This is all about work, energy, and power. Thank you, and see you in the next class.